Hi everybody, my name is Cristian Spolaore and I'm a software engineer at DNAssim. In this video, I would like to introduce to you DNAssim, our simulator for the entire procedure of encoding, storing and decoding data from DNA strands. At DNAssim, our mission consists in introducing information theory into the context of DNA storage in order to provide a fast and reliable technology for the storage industry. Moreover, we strongly believe that data manipulation is the only way which could lead to such a needed improvement, so that the current technology could overcome its limit and become available and attractive for the storage industry. Our proposal is based on three pillars. So, first of all, the modeling of noise via stochastic analysis of data, which could lead to substitution of biological experiments with easier to handle software simulations. Moreover, we focus on encoding and decoding schemes by bringing our expertise on error correction codes and erasure correction codes on the context of DNA storage. And finally, we put these two aspects together inside our simulator called DNAssim. So diving a little bit into the details of DNAssim, we found out that it is divided into three main parts. So there is the encoder, the noisy channel, and the decoder. The encoder takes as input some data, brings them to the binary domain, so only ones and zeros, applies an outer code which allows then reconstruction of the written information. And then we map bits into nucleotides, apply indexes in the formed DNA strands, and finally attach a primer. So we simulate closely the entire biological procedure. Then there is the application of noise introduced by the fact that information are stored into DNA strands that must be read when needed. And then we come to the decoding part. So here the previous operation are reversed. So we start from nucleobases. We remove primers. We perform some operations called clustering and trace reconstruction, which allows for an improvement in the quality of readings of our DNA strands. And we finally decode information with the ECC structure. The noise model is usually divided into two parts, PCR and IDS. So polymerase chain reaction introduces some noisy events, which are models with insertions, deletions, and substitutions, each of them characterized by a certain probability to occur. So this is exactly the same scheme as before, where noise channel has been expanded into polymerase chain reaction, perform certain amount of cycles, and then insertions, deletions, and substitutions. So encoding, noise, and decoding come together in our simulator, DNAssim, which is managed by a graphical user interface, where it is easier to insert all the needed parameters and options. Moreover, our GUI provides graphs and text output at the end of a simulation and shows also its progress. For further details about the way the GUI works, I strongly recommend you to subscribe to the devoted part in our site, DNAalgo.com. So in order to wrap up this introductory presentation, I would like to show you an example of the strength of our simulator. So let us assume that we want to perform two tests, number one and number two, with different parameters in order to see which is the most efficient for our aims. So we choose outer code A for test 1, while outer code B for test 2. Then we perform some tricks on code. So let it be A and C for test 1 and B and C for test 2. Then we have some common parameters, and then we have a different type of clustering. So clustering type A for the first test, type B for the second one. We insert all these options inside our GUI by taking care that some basic requirements are respected, such as the percentage of GNC, and we obtain a certain number of DNA strands, which is 20 in this case. We can analyze the outputs. So in this case, for test 1, after the clustering trace reconstruction operations, we have one missing strand and 173 errors before the decoding is applied. On the contrary, on test 2, we have 2 missing strands and 315 errors, as it is shown also on these graphs and data sheets. So actually, one would expect that test 1 will perform a lot better than test 2. But in our configuration, we chose different ECC for the two tests. And in this case, it turns out that the ECC chosen for test 2 was a lot stronger than the one chosen for test 1. And so in the second case, we are able to recover all the strands, so 20 strands, while in the first case, we recovered only 19 strands out of 20. And this is confirmed also by the metrics output by the GUI, which are related to the efficiency of the ECC. And these two metrics are bit error rate based on bits and frame error rate based on frames, which are code words. And they are 0 for test 2, meaning that we have no errors left, while they're greater than 0 for test 1. So this concludes this introduction. I hope you find it interesting and you enjoyed it. Thank you very much.